Hello everyone, in this lecture we will be going over an IMO 1992 problem. It's actually problem number 1. Here's a view of this problem. So find all integers p, q, r ordered in the following way such that p minus 1 times q1 minus 1 times r minus 1 is in fact a divisor of PQR minus 1. So let's go ahead and start with a change of variable here, and let's make the following substitutions, if you will. So let's call P minus 1 as X, Q minus 1 as Y, and R minus 1 as Z. So therefore our divisor becomes XYZ, as you can see, and this term here is simply well, obviously P is X plus 1, so therefore this expression will be just X plus 1 times Y plus 1 times Z plus 1 minus 1. So therefore equivalently, the problem is to show that for, well, obviously when p is strictly greater than 1, so it means x plus 1 is strictly greater than 1, suggesting that x itself is strictly greater than 0, or if you will, x is greater than or equal to 1, which is strictly less than y, which is strictly less than z. So z is the largest among those. So for these values, well, we would like to find those x, y, z such that so x, y, z perfectly divides, I should say, xy plus yz plus zx, so I'm just expanding this form here, plus x plus y plus z, and the plus 1 and minus 1 will cancel out, and that's the whole term here. Equivalently, further you can say, so it's possible to say that obviously if this divides this right hand expression here, it means xy plus yz plus zx plus x plus y plus z over xyz is in fact a positive integer. That suggests, have a look at this function here in 3 variables. F has x, y, and z variables, and you can rewrite this fraction as 1 over z plus 1 over x plus, so 1 over x, 1 over y, plus 1 over xy, 1 over yz plus 1 over zx plus 1 over xy. So f is a function like this in x, y, and z, and further f is a decreasing function in each of these variables x, y, and z. So in that case, in calculus notation, f1, f sub 2, and f sub 3 are all less than 0. So now by symmetry, and because those x, y, z's are distinct, so obviously from the conditions here, or I should say here, this condition here, so by symmetry and by those x, y, z's being distinct, this would imply that in fact f of x, y, z has an upper bound, so, and this upper bound is simply f of 1, 2, and 3, as you can see, because as I said, so those are the smallest numbers you can pick, and as you pick those smallest numbers, our function is the largest. But that's simply equal to, once you plug in these values here, that would give you 2 plus 5 over 6, I believe, which is obviously strictly less than 3. But that suggests that because our function can only accept integer values, f of x, y, z is either 1 or 2. So therefore, so we can have a look at those cases carefully. So let me open a new page and follow on that new page. So we know the values of the function f of x, y, z is 1 or 2. So equivalently, this can be represented as xy plus yz plus zx plus x plus y plus z is equal to k times xyz, if you will, for k is equal to 1 or 2. But then note also that f of 3, 4, 5 is equal to 59 over 60, and that's strictly less than 1. So for this case, x is in, well, it suggests that x must be either 1 or 2, because the presence of x being 3 or larger won't work. Our function is too small, so we need to pick smaller x values so that our function value will be higher, at least 1. And similarly, also note that f of, whenever we pick it as 2, 2, 3, 4, that's simply equal to 35 over 24, which is still less than 2. So that implies that whenever x is equal to 2, that necessarily implies that k is equal to 1. And when x is equal to 1, k might be either 1 or 2, as I said. So therefore, we actually have 3 cases after making this rough work. So when x is actually equal to 1 and k is equal to 1, in that case 1 plus 2 times y plus z plus y z is equal to yz, but that's not possible, so we can just rule that case out. That's not going to work. So the second case, we have that x is still 1 and k is equal to 2. In that case, we have 1 plus 2 times y plus z is equal to yz. We can factorize, so I should say y minus 2, not plus 2, unfortunately. So y minus 2 times z minus 2, that's equal to 5. And as a result from here, that's good. So it gives us xyz equals 1, 3, 7, I believe. But be reminded, so we are interested in the values of PQR, not XYZ. At the beginning, we did a change of variable, as you remember. So therefore, PQR in that case would simply be 1 more. So 2, 4, 8, because P was simply x plus 1, or x is P minus 1, if you will. And finally, case 3. X is equal to 2, and so when x is equal to 2, we know we are forcing k to be 1. In this case, we have the 2 plus 3 times y plus z is equal to yz. Again, we can factorize this as y minus 3 times z minus 3 is equal to 11. So we need to come up with 2 numbers. Their product is 11, so we can think of only one case where y is equal to 4 and z must be greater than y. So we know their order here, the ranking. So z must be better be 4. I believe it must be 14. So therefore that must be equal to 1, and that whole thing is equal to 11, suggesting that x, y, z is equal to x is equal to 2, obviously, y is 4, and z is 14. So therefore this suggests that PQR is equal to 3, 5, 15. And those are the two solutions to the given problem. So that solves our problem, and hope to see you in our next video.